Welcome to Astro Odyssey. Explore the universe. To truly understand the allure of the Venusian clouds, one must first confront the visceral terror of the surface. We often describe Venus as Earth's twin because of its nearly identical mass and gravity. But the comparison ends at the atmosphere. On the ground, the pressure is 90 times that of Earth. If you were to stand there unprotected, the atmosphere would not merely weigh on you, would crush you with the same force felt 3,000 feet beneath the ocean's surface. This is an environment where the laws of chemistry and physics seem to warp. At these pressures, carbon dioxide becomes a supercritical fluid, a bizarre state of matter that has the properties of both a gas and a liquid. It is a world where the air ripples like water, but flows like a breeze, scouring the basaltic plains with a slow, relentless density. The heat for 175 degrees Celsius, 900 degrees Fahrenheit, is not a temporary peak. It is a global constant maintained by the most runaway greenhouse effect in the solar system. There is no relief at the poles and no respite at night. The Soviet Venera landers of the 1970s and 80s were masterpieces of engineering, essentially armored diving bells built to withstand the crushing weight. Even so, the longest lived among them, Venera 13, survived for only 127 minutes. It sent back grainy, yellowish photos of a jagged, orange landscape before its internal electronics literally melted into a puddle of silicon and solder. For 40 years, this image is scorched. Suffocating graveyard has defined our relationship with Venus. We saw it as a warning of what Earth could become, a cautionary tale written in acid and fire. However, the tragedy of our exploration history is that we focused on the floor of the room rather than the air within it. If we look at Venus not as a solid destination, but as a multi-layered volume, the perspective shifts. As you ascend from the surface, the conditions change with a predictability that is almost eerie. At 30 kilometers up, the pressure is still high, but the heat begins to dissipate. At 40 kilometers, the caustic sulfuric acid clouds begin to thin, revealing a world of amber light. But it is at the 50 to 60 kilometer mark that the miracle occurs. Here, the atmosphere of Venus is, for lack of a better word, earthly. The temperature ranges between 0 degrees Celsius and 50 degrees Celsius. The pressure is exactly 1 bar, the same pressure you feel at a beach on Earth. This habitable zone is the only place in the solar system, other than Earth, where a human could step outside a cabin without a pressurized suit. You would still need an oxygen mask and protection from the acidity of the surrounding mist. But your body wouldn't explode or implode. You wouldn't boil or freeze. In fact, if you were standing on the balcony of a floating gondola at this altitude, you could wear a simple jumpsuit, a breathing apparatus, and feel perfectly comfortable. This leads us to the most startling realization in planetary science. On Venus, breathable air is a lifting gas. On Earth, we use helium or hydrogen to make balloons float because those gases are lighter than our nitrogen-oxygen atmosphere. But the atmosphere of Venus is mostly carbon dioxide, which is much heavier than the air we breathe. This means that a giant spherical envelope filled with ordinary Earth air, 78% nitrogen, 21% oxygen would naturally float in the Venusian clouds. The air that keeps you alive also provides the buoyancy to keep your city aloft. A colony on Venus wouldn't be a cramped, pressurized tin can like a base on Mars. It would be a massive soaring structure. A geodesic dome 2 kilometers in diameter could lift hundreds of thousands of tons of equipment and thousands of people. If the envelope were breached, there would be no explosive decompression. Instead, the pressure inside and outside would be the same, and the gases would simply slowly mix, giving engineers hours or even days to patch the leak. The high-altitude Venus operational concept, HAVOC, proposed by NASA researchers, represents the first serious blueprint for this vision. It envisions massive, helium-filled airships that would eventually be replaced by permanent, oxygen-filled habitats. Material science is the key to this transition. While sulfuric acid is corrosive, we already have materials like Teflon and various polymers that are entirely resistant to it. A city on Venus would be wrapped in a skin of acid-resistant plastic, glowing white or silver to reflect the intense solar radiation from above. Because Venus is closer to the sun than Earth's solar panels would be twice as effective here as they are on our home planet. Furthermore, the thick atmosphere reflects so much light that you could place panels on the bottom of your floating city to catch the light. Bouncing off the clouds below, the potential of Venus extends beyond mere survival. It touches on the possibility of indigenous life. In recent years, the detection of phosphine and other anomalous chemicals in the Venusian cloud decks has sparked a fierce debate among astrobiologists. While the surface is a sterile furnace, the clouds are a chemical playground. Water vapor, though scarce, exists in the clouds. There is abundant carbon, sulfur, and sunlight. If life exists elsewhere in the solar system, it may not be in the frozen oceans of Europa or the dusty plains of Mars, but in the acidic mists of Venus microbes that have evolved to live, eat, and reproduce without ever touching the ground. By building floating colonies, we wouldn't just be visiting a planet. We would be entering an ecosystem. We'd become a cloud-faring species. This shift represents the ultimate irony of space exploration. We spent decades looking down at the hell of the Venusian surface, never realizing that just a few miles above our heads, the heavens were waiting for us. The mid-20th century was defined by a binary choice that would shape the trajectory of human exploration for 70 years. The choice between the red planet and the morning star. While the public imagination was captured by the cold, romantic desolation of Mars, Venus was relegated to a secondary statassa, difficult planet that offered no easy victories. This period of the space race created a divergent path in planetary science. United States, fueled by the visionary goals of the Apollo program, viewed Mars as the logical next step for a terrestrial species. Mars was a world of horizons, of dust storms that looked like Earth's deserts, and of ancient riverbeds that whispered of a familiar past. Venus, conversely, was an opaque enigma, wrapped in a shroud of clouds that defied the most powerful telescopes of the era. While NASA looked toward the Moon and Mars, the Soviet Union embarked on what remains the most punishing engineering campaign in history, the Venera program. To the Soviet scientists of the 1960s, Venus was not a cautionary tale. It was the ultimate test of material science and ideological resolve. They realized early on that Venus would not yield its secrets to the delicate, spindly probes used for lunar flybys. To touch Venus was to enter a combat zone where the enemy was the air itself. The early failures of the Venera program are a testament to how little we understood the sheer violence of the Venusian environment. Probes were crushed like soda cans before they even reached the ground, their hulls buckling as the pressure rose exponentially during the descent. It wasn't until Venera 7 in 1970 that a human-made object finally broadcasted from the surface of another planet. It survived for only 23 minutes of frantic, desperate burst of data sent through a failing transmitter before the probe was literally flattened into the basalt. Those 23 minutes represented a triumph of the human spirit over physics, yet they also served to reinforce the evil twin narrative. The data revealed a world that felt fundamentally anti-life. By the time Venera 13 landed in 1982, the Soviets had mastered the art of the planetary diving bell. They built probes with titanium hulls, internal cooling systems using phase change materials, and specialized lenses that could withstand the caustic haze. Venera 13 gave us the Golden Photos panoramic, images that remain our only ground-level view of this alien world. These images are haunting. They depict a landscape of flat, jagged rocks under a sky the color of a bruised orange. The light is diffused, shadowless, and heavy. It looks like a vision of the bottom of an acidic ocean. When these images reached Earth, they didn't inspire a new wave of exploration. They inspired a collective shudder. Compared to the higher resolution, blue sky simulated photos coming back from the Viking landers on Mars, Venus looked like a graveyard. We are an aesthetic species, and we fell victim to an aesthetic bias. Mars offered us a fixer-upper world cold, yes, but one where a human could imagine walking with a simple pressure suit. Venus offered us a furnace. We mistook a hostile surface for a hostile planet. We saw the locked door of the surface and assumed the entire house was on fire. Following the collapse of the Soviet Union, the drive to penetrate the Venusian atmosphere evaporated. For nearly 30 years, Venus became the forgotten planet. While we sent a fleet of rovers to Mars Spirit, Opportunity, Curiosity, and Perseverance, Venus received only the occasional flyby or a long distance radar mapping mission like NASA's Magellan. Magellan's radar was revolutionary, stripping away the clouds to reveal a surface dominated by massive shield volcanoes and strange tessera terendiformed highlands that are older than the rest of the planet's crust. But because Magellan could not see through the atmosphere and the visible spectrum, the planet remained an abstract data point. We settled into a comfortable ignorance, assuming that because the surface was dead, the planet's history was static. We missed the biggest clue in the solar system, the fact that for nearly 3 billion years, Venus likely had liquid water oceans. It was probably the first habitable world in our solar system, potentially supporting life long before Earth's own environment stabilized. By turning away from Venus because it was too hard, we ignored the most important chapter in the biography of our own home. We treated Venus as a failed Earth, when in reality, it may be the most successful laboratory for atmospheric physics we have ever encountered. The narrative of Venus as a born failure has been the bedrock of planetary science for decades. We long assumed that because Venus sits closer to the Sun, at the inner edge of the habitable zone, it was doomed from the start. We imagined it as a world that never had a chance. A place where the heat was so intense from day one that water could never settle into liquid form. But the climate modeling breakthroughs of 2025 and 2026 have shattered this assumption, revealing a history that is far more tragic and far more familiar than we ever dared to dream. The emerging data suggests that for the vast majority of its life, Venus was not a hellscape. It was a garden. 4 billion years ago, a traveler entering our solar system would have seen not one, but two blue marbles. Earth and Venus were nearly identical in their infancy. Both planets were born from the same cloud of gas and dust. Both were endowed with massive inventories of water, delivered by icy comets and volcanic outgassing. New simulations, utilizing the hyper-accurate atmospheric data from recent deep space probes, indicate that Venus likely possessed vast, shallow oceans and a temperate climate. Crucially, this wasn't a fleeting phase. While Mars lost its water in a geological heartbeat within its first billion years, Venus may have held on to its oceans for 3 billion years. To put that into perspective, life on Earth began in the oceans roughly 3.5 to 4 billion years ago. If Venus had liquid water for 3 billion years, it means that for nearly 75% of its history, the planet was perfectly hospitable. It wasn't just a wet period. It was an era of stability long enough for complex life to have potentially crawled out of the Venusian seas and onto its ancient continents. The divergence between Earth and Venus, the moment one became a paradise and the other a tomb, came down to the mechanics of a global thermostat. On Earth, we are protected by a complex cycle known as the carbonate-silicate cycle. When carbon dioxide enters our atmosphere, it is washed out by rain, flows into the oceans, and eventually gets trapped in seafloor rocks through plate tectonics. Our planet has a drain for its greenhouse gases. Venus, for reasons we are still investigating, lacked this structural luck. It may have started with a slower rotation, or perhaps its lack of a massive moon like our own prevented the tidal forces necessary to keep its internal plate tectonics lubricated. Without a magnetic field to protect it, the upper atmosphere was constantly battered by solar winds. As the young sun aged, it naturally grew brighter and hotter. On Earth, the thermostat adjusted. On Venus, the temperature reached a critical threshold where the oceans began to evaporate at an accelerated rate. This was the beginning of the runaway greenhouse effect, a planetary death spiral. Water vapor is an incredibly efficient greenhouse gas, far more potent than carbon dioxide. As the oceans turned to steam, they trapped more heat, which caused more evaporation, which trapped even more heat. This feedback loop was relentless. The heat eventually became so intense that it did something horrifying to the very crust of the planet. On Earth, water acts as a lubricant for tectonic plates, allowing them to slide and grind. On Venus, the heat baked the water out of the rocks. The crust became stiff and immobile, effectively locking the planet's surface. Without tectonics to bury carbon, the volcanoes of Venus massive. Towering vents continued to pump carbon dioxide into the sky, with no way for it to be reabsorbed. In a geological blink of an eye, the oceans were gone. The hydrogen was stripped away into space by solar winds, leaving behind a thick, suffocating blanket of carbon dioxide. The lush oceanic world was vomited into the atmosphere, creating the $90 bar pressure cooker we see today. By deconstructing this ancient catastrophe, we realize that Venus is not just a distant curiosity. It is a mirror. It represents the high security wing of planetary evolution, a warning of what happens when a planet's delicate atmospheric balance is shattered. We used to look at Venus and see a world that was simply wrong. We see a world that was right for billions of years, only to be undone by a shift in its feedback loops. It teaches us that habitability is not a permanent state. It is a dynamic equilibrium. Understanding the divergence of the 3-billion-year ocean is no longer just about space exploration. It is about understanding the fragility of our own home. If we can figure out exactly when and why the Venusian thermostat broke, we might gain the knowledge necessary to ensure Earth's own remains intact. In the autumn of 2020, as humanity found itself locked in a struggle against a terrestrial biological threat, the eyes of the scientific community were pulled upward by a ghostly signal from the morning star. The announcement was led by Professor Jane Greaves of Cardiff University, and it landed with the force of a tectonic shift. Using the James Clerk Maxwell Telescope JCMT in Hawaii and the massive Atacama Large Millimeter Submillimeter Array ALMA in Chile, her team had identified a specific razor-thin frequency in the spectrum of light, reflecting off the Venusian clouds. That frequency belonged to phosphine pH 3. To the layperson, phosphine sounds like a mundane chemical footnote. It is a colorless, flammable, and highly toxic gas that smells of rotting fish or garlic. But in the specialized language of astrobiology, phosphine is a holy grail. It is a chemical that, on a rocky planet like Venus, serves as a digital fingerprint for life. The discovery suggested that the yellow haze we had long dismissed as a sterile acid bath might actually be an inhabited biosphere. The reason phosphine caused such an immediate and polarized firestorm in the scientific community is rooted in the laws of chemistry. Phosphine is a high-energy molecule. On a planet dominated by oxygen and sulfur, phosphorus prefers to be in a low-energy state, bound to oxygen as phosphates. To force phosphorus atoms to bond with hydrogen instead requires a massive input of energy, or a very specific set of biological circumstances. On gas giants like Jupiter and Saturn, phosphine exists because the sheer crushing pressure and internal heat of the planet's deep interior act as a forge, forcing the atoms together. But Venus is a terrestrial, rocky world. It lacks the internal pressures of a gas giant. According to every model of standard planetary chemistry, there is no known geological or atmospheric process, not lightning, not volcanic activity, not even meteor impacts that could produce phosphine in the concentrations Greaves and her team detected on Earth. Phosphine is almost exclusively a biogenic product. It is produced by anaerobic bacteria microbes that live in oxygen-starved environments like sewage plants, marshlands, and the intestinal tracts of animals. If you find phosphine on a rocky planet, you are looking at a ghost in the machine, a chemical byproduct of a metabolism. What made the 2020 discovery even more provocative was the lifespan of the molecule. Phosphine is chemically unstable in the Venusian environment. The clouds of Venus are saturated with ultraviolet radiation from the sun and filled with sulfuric acid, both of which should tear phosphine molecules apart within minutes. The fact that it was detected at all implies a continuous source. Something in the clouds of Venus must be actively pumping phosphine into the atmosphere at a rate that offsets its rapid destruction. This realization eliminated the possibility that the gas was a relic from the planet's ancient oceanic past. Whatever was creating that phosphine was alive or at least active now. The discovery forced a frantic revaluation of our atmospheric models. Skeptics argued that the signal might be a misidentification of sulfur dioxide, or that there was some unknown exotic chemistry at play that didn't involve life. Yet, as the data was poked, prodded, and reanalyzed over the following years, the phosphine signal remained stubbornly present in several subsequent observations. It refused to be debunked easily. The phosphine discovery transformed the Venusian paradox from a geological curiosity into a biological mystery. If there are microbes in the clouds, how do they survive? The clouds are not just water. They are droplets of 80% concentrated sulfuric acid, ASTROBIOLOGISTS, began to propose radical new models for Venusian life. They envisioned microbes encased in acid-resistant, protective shells, perhaps utilizing sulfur itself as a source of energy. These organisms would never touch the ground. They would live out their entire life cycles, suspended in the air, riding the massive, planet-wide winds that circulate the Venusian atmosphere every 4 Earth days. This brings us back to the tragic history of the planet. If Venus had oceans for 3 billion years, life had ample time to evolve. As the oceans boiled away and the surface became a furnace, any surviving life would have had only one place to go: up. The phosphine signal may be the last desperate whisper of an ancient civilization of microbes, the descendants of an oceanic world that refused to die, even when the world beneath them turned to hell. the announcement of phosphine wasn't greeted with a universal eureka. Instead, it ignited one of the most intense scientific skirmishes of the 21st century period, now known as the War of Data. From 2021 through 2024, the halls of academia and the servers of preprint journals became a battlefield. The stakes were nothing less than the first discovery of extraterrestrial life. And in science, extraordinary claims require not just extraordinary evidence, but evidence that can survive a relentless gauntlet of peer review fire. The skepticism was rooted in the sheer difficulty of observing a planet through a thick, turbulent atmosphere from millions of miles away. Critics pointed to the complexity of the ALAMA data processing. To isolate the faint signal of phosphine, researchers had to strip away layers of noise from the background radiation of the solar system. Some independent teams, upon reanalyzing the raw data, claimed the signal was an artifact, a ghost created by the very software used to find it. Others suggested a case of mistaken identity. Sulfur dioxide, SO2, a gas abundant in the Venusian atmosphere, has a spectral signature that sits incredibly close to that of phosphine. Skeptics argued that Greaves and her team hadn't found life. They had simply found a particularly thick patch of volcanic gas. For a time, it seemed the phosphine discovery would be relegated to the false alarm bin of history, a cautionary tale about the dangers of seeing what we hope to find. However, the narrative took a stunning turn in early 2026, armed with more sensitive receivers and the benefit of more stable observation windows from the upgraded James Clerk Maxwell telescope. Researchers didn't just find the signal again, they found its rhythm. The 2026 data revealed that phosphine levels on Venus are not static. They are variable. The War of Data shifted from a debate over whether the signal existed to an investigation into why it was fluctuating. The telescope captured a cycle that felt hauntingly familiar. The phosphine concentrations appear to bloom at dawn and dusk, reaching their peak as sunlight hits the mid-cloud layers, only to fade during the long Venusian night. In the cold logic of chemistry, gases don't usually care what time it is. In the logic of biology, the time of day is everything. This variability was the smoking gun the scientific community needed to move the conversation from pure chemistry into the realm of ecology. On Earth, we see this exact behavior in our own atmosphere. Methane levels rise and fall with the seasons and the day-night cycle as plants photosynthesize. Animals move and microbes decay. We call this a biogenic flux. On Venus, this phosphine cycle suggests a biological population that reacts to its environment. Imagine a layer of microorganisms suspended 50 kilometers up. As the sun rises, these aerial extremophiles might rise to the upper reaches of their cloud layer to harvest solar energy or engage in metabolic processes, producing phosphine as a byproduct. As the sun sets and the temperature shifts, they might enter a dormant state or sink into lower, more protected mists to avoid the radiation of open space. The discovery of this rhythm changed the fundamental question of the mission. We are no longer just looking for a molecule. We are looking for a pulse. The ghost in the machine has a heartbeat, and it is synchronized with the rotation of the planet itself. This realization has turned Venus from a dead laboratory into a living, breathing puzzle, forcing us to consider that the evil twin might not be a graveyard, but a vast, floating forest of microscopic life. If the 2020 discovery of phosphine provided the smoke, then the 2025 detection of ammonia NH3 provided the fire. 4 years. The greatest argument against life on Venus was the sheer acidity of its environment. The Venusian clouds are not fluffy water vapor formations like those on Earth. They are concentrated mists of sulfuric acid H2SO4 with a pH level often falling below 0. This is a landscape where the rain can dissolve steel, let alone the delicate proteins and lipids that make up a living cell. To any Earth-based organism, the Venusian clouds are a liquid death sentence. Yet, the discovery of ammonia has introduced a radical new chapter in our understanding of planetary biology. Ammonia is a base, the chemical antithesis of acid. In a world defined by its acidity, the presence of a neutralizing base is a chemical glitch that demands an explanation. In the high-stakes world of Venusian chemistry, ammonia shouldn't exist in significant quantities. It is a nitrogen-hydrogen compound that should be instantly obliterated or neutralized by the surrounding acid. Its persistent presence suggests a deliberate chemical intervention. This has led to the neutralization theory, concept that reimagines the Venusian microbe not as a victim of its environment, but as a master of it. If a microbe in the clouds were to produce ammonia as a byproduct of its metabolism, it could effectively create a chemical shield by releasing ammonia. The organism could neutralize the sulfuric acid within its immediate vicinity, turning a droplet of lethal acid into a salty, liquid microbubble with a pH survivable for life. This isn't just survival. It is environmental engineering at a microscopic scale. The ammonia isn't just an accident. It is a life support system. This chemical mastery allows for a fascinating biological rhythm known as the Venusian cloud life cycle. Scientists now hypothesize that life on Venus does not stay in one place. It participates in a massive, vertical migration that spans the entire atmospheric column. The cycle likely begins in the lower, hotter layers of the atmosphere at the haze below the main cloud deck. Here, conditions are too extreme even for the neutralizers. In this region, life might exist as desiccated sporstini, dried-out biological seeds that are light enough to be caught by the planet's powerful thermal currents. As the heat rises from the scorched surface, it carries these spores upward, like dust motes on a draft. When these spores reach the habitable zone 50 to 60 kilometers up, they encounter moisture and more temperate conditions. This is the wake-up call: hydration. The spores absorb water and trace nutrients from the surrounding mist. Activation. The microbes begin their metabolic processes, immediately pumping out ammonia to neutralize their acid droplets. The bloom, protected in their neutralized bubbles. The microbes feast on the abundant ultraviolet light from the sun and the chemical energy of the sulfur-rich air. This is when the phosphine blooms occur, signaling a peak in biological activity. The descent. As the microbes grow and multiply, the droplets they inhabit eventually become too heavy to remain buoyant. They begin to sink back toward the furnace below. Desiccation as they fall into the hotter, drier layers. The microbes shed their water and return to a spore state, drifting back down to wait for the next thermal current to carry them back to the sky. This model suggests that we aren't just looking for a single, lonely cell or a random patch of mold. We are looking for a planet-wide atmospheric engine. Venus has turned its entire sky into a conveyor belt for life. The sulfuric acid, once thought to be a barrier to existence, may actually be the medium that stores and protects these organisms as they travel. By finding ammonia, we have found the thermostat of the Venusian biosphere. It is the signature of a species that has learned to live in the belly of the beast by changing the chemistry of the beast itself. We are looking at a world where life has not merely survived a catastrophe, but has evolved to treat a lethal atmosphere as its permanent, thriving home. The culmination of decades of comfortable ignorance is finally coming to an end with the launch of the Da Vinci mission, short for Deep Atmosphere Venus Investigation of Noble Gases, Chemistry, and Imaging. Da Vinci is not merely a satellite, it is a high-tech sacrifice. It is a titanium descent sphere, a literal diving bell designed to survive a journey through a gas ocean. While previous missions have peeked at Venus from a distance or bounced radar off its clouds, Da Vinci is designed to taste the planet, to breathe in its history, and to see the forbidden landscape beneath the haze. The mission's descent will last roughly 1 hour, a tense 60-minute plunge through the most corrosive environment in the solar system. During this time, the probe will act as a master chemist. It is equipped with a sophisticated mass spectrometer and a tunable laser sensor, designed to sniff the atmosphere at every kilometer of altitude. Specifically, Da Vinci is hunting for noble gases like xenon, krypton, and neon. These gases are chemically inert, meaning they don't react with other elements. They act as primal fingerprints, locked in the atmosphere since the planet's formation. By measuring the ratios of these gases, scientists can reconstruct the timeline of the Venusian atmosphere. This will provide the definitive proof we have been seeking. Did Venus truly possess an ocean for 3 billion years? If the ratios of heavy isotopes match the signatures of ancient water laws, the 3 billion-year ocean theory will move from hypothesis to historical fact. As the probe survives the chemical gauntlet of the mid-clouds, it begins the most cinematic phase of its journey. At about 30 kilometers above the surface, the atmosphere becomes so thick that it behaves more like a liquid than a gas. Light begins to bend in strange ways, and the temperature rises to levels that would melt lead. But it is here, beneath the opaque cloud deck that has hidden the surface for eons, that Da Vinci's cameras will finally hum to life. The target is Alpha Regio, a region of tessera terrain. These are the most ancient geological features on the planet Jagged. Folded highlands that look like the crumpled paper of a cosmic giant. To many geologists, these are the lost continents of Venus, on Earth. Continents are formed through the interaction of water and plate tectonics. If Alpha Regio's chemical composition shows evidence of granite or other water-formed rocks, we will be looking at the dried-up remains of a world that once looked exactly like our own. The climax of the mission occurs in the final 15 minutes. As the probe nears the surface, it will capture high-resolution, three-dimensional images of the terrain. For the first time, we will see the evil twin in staggering detail, not through grainy radar, but through the clear eye of a digital camera. We will see the ridges, the valleys, and perhaps the dry riverbeds of a drowned world. Then the mission ends. There is no parachute that can survive the final impact, no cooling system that can withstand the 900-degree Fahrenheit heat for long. Da Vinci will hit the surface of Alpha Regio at a speed of roughly 12 meters per second. It may survive for a few minutes on the ground, sending back one last burst of data from the scorching basalt, before the electronics succumb to the pressure and heat. But those final minutes will change everything. In the brief lifespan of a single probe, we will bridge a gap of billions of years. We will have touched the history of a planet that tried to kill our curiosity, and in doing so, we will finally understand that the story of Venus is not a story of a distant stranger. It is the story of our own potential future, written in the rocks of a world that once had everything, while Da Vinci plunges through the atmosphere to taste the Venusian air. The Veritas orbiter will remain high above, performing a technological feat akin to a planetary X-ray. Veritasen, acronym for Venus, emissivity, radioscience, NSAR, topography, and spectroscopy is designed to peel back the opaque shroud of sulfuric acid and reveal the bones of the planet beneath. It is our first return to global Venusian mapping since the Magellan mission of the early 1990s. But the jump in technology is like moving from a hand-drawn map to a live satellite feed. The central question Veritas aims to answer is whether Venus is a static tomb or a dynamic sister. For decades, we viewed Venus as a geologically dead world, a planet that had frozen its surface features millions of years ago. However, in 2023 and 2024, a revolutionary reanalysis of 30-year-old Magellan data changed everything. Scientists manually comparing radar images from 1991 discovered a volcanic vent near Mont Mons that had visibly changed shape and doubled in size. Over a period of just 8 months, this was the first smoking gun of active volcanism on Venus. It suggested that the planet is not a relic of the past, but a world that is breathing, shifting, and erupting right now. Veritas is built specifically to find these heartbeats. Using interferometric synthetic aperture radar (NSAR), the orbiter will measure changes in the surface elevation with a precision of just 1.5 centimeters. If a plume of magma pushes the ground upward, or if a Venusquake causes a fault line to slip, Veritas will see it in real time. The challenge of Venus has always been its clouds, which block almost all visible light. But Veritas carries a secret weapon: the Venus Emissivity Mapper, VM. This spectrometer operates in specific spectral windows, narrow bands of infrared light that the Venusian atmosphere is actually transparent to. By looking through these windows, Veritas can see the thermal glow of the surface. It will search for hotspots, areas of the crust that are significantly hotter than their surroundings, indicating fresh lava flows or active volcanic vents. Furthermore, it will map the mineral composition of the entire planet. If it finds rocks like granite in the Highland Tesserae, it will prove that these regions are indeed the continents of a lost oceanic world. As granite requires water to form, the data from Veritas will do more than just map mountains. It will explain why Earth and Venus diverged. On Earth, plate tectonics act as a cooling system, releasing internal heat and recycling carbon. We don't yet know if Venus has a similar process, or if it releases its heat in violent, planet-wide bursts of volcanic activity. By measuring the planet's gravity field to an unprecedented level of accuracy, Veritas will allow us to see into the core. We will finally know if the Venusian center is liquid or solid, and how much heat is still trapped inside. If Venus is still geologically active, it means the planet is still evolving. It means that the evil twin isn't a finished story. It's a living laboratory of atmospheric and geological extremes. Veritas will provide the final piece of the puzzle, proving that Venus is not just a warning of what Earth could become, but a vibrant, active world that still has secrets to tell. When we speak of colonizing the stars, our minds almost instinctively drift to the red dust of Mars, driven by a terrestrial bias that demands a solid surface beneath our feet. But a growing contingency of aerospace engineers argues that we have been looking at the wrong planet. Enter NASA's HAVOC, the High-Altitude Venus Operational Concept. This isn't science fiction. It is a rigorous, phased engineering roadmap for a city in the sky that challenges our very definition of habitation. While the surface of Venus is a pressure cooker that destroys titanium, the atmosphere at 50 kilometers above the ground is the most hospitable environment in the solar system outside of Earth itself. The core of the HAVOC concept relies on a startling chemical reality. On Venus, breathable air is a lifting gas. Because the Venusian atmosphere is roughly 96% dense carbon dioxide, a mixture of 78% nitrogen and 21% oxygen, the very air you are breathing right now is significantly lighter than the surrounding environment. In fact, it provides about half the lifting power that helium provides on Earth. This creates an engineering cheat code. In a Martian colony, every cubic meter of breathable air is a liability of pressurized gas constantly trying to explode outward into the vacuum. On Venus, every cubic meter of air is an acetate, is the very thing that keeps your city afloat. A massive geodesic sphere, or a dirigible, filled with Earth standard air would naturally seek an equilibrium at the 50-kilometer mark, where the external pressure is a perfect one. One of the most profound arguments for the aerial frontier is the issue of human health. Mars has two silent killers that Venus lacks: low gravity and radiation. Martian settlers would live in 0.38 gram, condition likely to cause irreversible bone density loss and muscle atrophy over years of habitation. In the Venusian clouds, however, the gravity is $0, 9G, nearly identical to Earth. A child born in a Venusian cloud city would grow up with a skeletal structure capable of visiting Earth without being crushed by its own weight. Furthermore, Venus possesses a massive, thick atmosphere that serves as a natural lead-lined shield, while Mars is constantly hammered by solar flares and cosmic rays, forcing settlers to live in windowless underground lava tubes. The $50 kilometers of air above a Venusian colony provide the same radiation protection as Earth's atmosphere. You wouldn't be hiding in a cave. You would be living in a skylight-filled atrium, bathed in the diffuse, golden light of the sun. The HAVOC roadmap envisions an evolutionary path, starting with robotic aerobots and culminating in permanent, miles-long floating research hubs. The primary challenge is not the heat or the pressure, but the sulfuric acid mist. To combat this, engineers have turned to specialized polymers. Materials like FEP Teflon have already been tested in concentrated acid baths and shown to maintain 90% transparency, allowing for the creation of acid-resistant envelopes that double as giant solar arrays in these floating outposts. The outdoors becomes accessible in a way that is impossible on any other world. Because the pressure is equalized, a colonist could step out onto an external observation deck, wearing nothing more than a lightweight, chemically resistant jumpsuit and a simple breathing mask. There is no risk of explosive decompression. If the envelope were to suffer a tear, the air would leak out so slowly that residents would have days or even weeks. To patch it, Venus forces us to abandon the pioneer model of claiming land and replace it with a maritime model of sailing the winds. It is a world where we don't conquer the ground. We inhabit the sky. As solar technology becomes more efficient and carbon nanotube materials allow for even larger structures, the dream of Hawk transforms from a 30-day mission into a permanent civilization. We may one day look up from Earth and know that our twin planet is no longer a dead warning, but a bustling network of floating cities, drifting forever through the amber mists of a world we finally understood. The study of Venus is not merely an act of local curiosity or a nostalgic look at a failed Earth. It is the cornerstone of our understanding of the entire galaxy. As we enter the golden age of exoplanetary discovery, Venus has moved from being a planetary outlier to becoming the most important control group in the search for life. With instruments like the James Webb Space Telescope, JWST, and the upcoming Nancy Grace Roman Space Telescope, peering into the deep reaches of the Milky Way, we are discovering that the universe is not just filled with planets, but specifically with exovenuses, Earth-sized worlds orbiting at the inner edges of their stars' habitable zones. Currently, our data on these distant worlds is agonizingly thin. We see them primarily through transit spectroscopy, watching as a planet passes in front of its star, and analyzing the thin sliver of starlight that filters through its atmosphere. From 40 light-years away, an Earth and a Venus look nearly identical. Both are rocky, both have similar diameters. and both sit in the Goldilocks region of their respective systems. Without the lessons learned from our own neighborhood, we would be flying blind. If we cannot decipher the complex, non-equilibrium chemistry of the Venus in our own backyard, we have no hope of identifying habitable worlds across the galaxy. Venus serves as the Rosetta Stone for atmospheric physics. It teaches us how to identify the spectral fingerprints of a runaway greenhouse effect. By studying the way sulfuric acid and carbon dioxide interact with sunlight on Venus, we create the templates that allow us to look at a planet light years away and say, with confidence, that world is a furnace, not a forest. The discovery of phosphine and ammonia on Venus has heightened the stakes of this cosmic calibration. If we can prove that these chemicals are being produced by an aerial biosphere on Venus, it completely redefines our criteria for a habitable planet. It suggests that the habitable zone is not just a flat ring on a map where liquid water can sit on a surface, but a three-dimensional volume that can exist high in the atmosphere of even the most hostile worlds. By solving the mystery of the phosphine in our own neighborhood, we are essentially zeroing our instruments. We are learning how to distinguish between a biosignature, a gas produced by life, and a geosignature, a gas produced by exotic, volcanic, or atmospheric chemistry. If we find phosphine on an exoplanet tomorrow, we would have no way of knowing what it means without the ground truth. It's provided by our proximity to Venus. Venus represents the inner boundary of life's possibilities. It teaches us the limits of atmospheric stability and the point at which a planet's thermostat breaks beyond repair. As we look at M-dwarf stars, the most common stars in the galaxy, we see that many of their planets are tidally locked, with one side in permanent day and the other in permanent night. Venus, with its incredibly slow rotation and super-rotating atmosphere, is the closest analog we have to these eyeball planets. We study Venus to ensure that when we finally point our greatest telescopes at a distant twin, we truly understand what we are seeing. We are moving from a period of discovery to a period of characterization. Venus is the laboratory where we test our theories of climate, chemistry, and biology before we apply them to the rest of the universe. In a very real sense, the road to finding Earth 2.0 begins with a deep, uncompromising look at the planet we once called our evil twin. In conclusion, we must return our gaze to the planet from which we started. Venus stands as a haunting, billion-year-old warning, a mirror reflecting the fragility of the planetary balance. It is a testament to what happens when a world's thermostat is broken, when the delicate cycles of carbon and water are pushed past the point of no return, but it is also a source of profound hope. If life has found a way to survive in the acidic clouds of such a hellish world, it suggests that life is far more resilient and creative than we ever dared to imagine. The realization that Venus may be inhabited or was once a lush, oceanic paradise shifts our entire understanding of biology. On Earth, we often think of life as a fragile flame that requires the perfect Goldilocks conditions to persist. Venus suggests that life is more like a flood. Once it takes hold, finds every crack and crevice, adapting to environments we once deemed impossible. If the neutralizing microbes of the Venusian clouds are real, they represent a triumph of evolution over entropy. They tell us that even when a planet's surface becomes a furnace, the story of life does not necessarily end. It simply moves to the sky. We are the first generation of humans with the technology to see through the clouds, to touch the surface, and to sniff the air of another world's history. The coming years represent a frantic, multinational gold rush to the morning star. While flagship missions like NASA's Da Vinci and Veritas are setting the stage for the 2030s, the 2026 launch window has become the immediate frontline. Private ventures, such as the Rocket Lab MIT Venus Life Finder, are currently preparing for a summer 2026 launch. This mission aims to be the first private probe to enter the Venusian atmosphere, equipped with a specialized laser to detect the autofluorescence of organic molecules. Unlike the heavy, multi-billion-dollar probes of the past, this Night Sand Weekends project represents a new era of agile, low-cost exploration. It is a scout sent to answer one specific question. Are we alone in our own backyard? What we find there in the coming decade will do more than just add data to a textbook. It will change our fundamental definition of life itself. By studying the runaway greenhouse effect of Venus, we are essentially studying our own potential future. The data we gather on atmospheric collapse and carbon cycles on Venus is directly applicable to our climate models on Earth. Venus is not just a destination. It is a laboratory for planetary preservation. We are no longer a species confined to one blue marble. We are a species beginning to understand the diversity of the cosmic family. Venus, our long-ignored twin, is finally ready to tell its story. It is a story of catastrophic loss and perhaps of microscopic survival. In its amber light, we see both the end of one path and the beginning of another. And in its story, we may just find the key to our own survival, not just as inhabitants of Earth, but as a spacefaring species capable of turning a warning into a hope.